If the universe can be described by physical laws, can those laws explain why a universe exists at all?
Wow. Well, that is arguably the most ambitious question a human being can even attempt to answer. I mean, it demands that we take the very tools we use to measure, say, a falling apple, or the spin of a single electron, and just stretch them across the absolute entirety of existence.
Right. And that is the exact mission for our deep dive today. We are exploring the ultimate questions of existence. Like, why is there a universe rather than just nothing?
Yeah.
Why do the physical laws that govern it take the highly specific forms that they do? And perhaps most significantly for us, why are we here to observe them in the first place?
It's massive.
It really is. So if you are listening to this right now, whether you were driving or cooking or just, sitting in a chair staring at the ceiling, consider this your shortcut to being genuinely well-informed on some of the most massive, mind-bending concepts in modern science. We are going to decode the dense math into clear, visual ideas.
But, and this is important, we are going to do it without oversimplifying the profound mysteries at the heart of it all. We aren't going to cheat you out of the complex details.
Exactly.
To do that effectively, though, we have to establish a vital intellectual baseline right from the start. Because when we try to answer these ultimate questions scientifically, we fundamentally change the standards of what actually counts as an answer.
Right. The whole metric shifts.
Exactly. The tension we are going to explore today, like the intellectual tightrope we are walking, is between immense ambition and necessary restraint.
Ambition and restraint. Unpack that a bit.
Well, on one hand, cosmology has this incredible ambition of seeking a comprehensive account of everything. But on the other hand, we must exercise restraint. We have to acknowledge that every single scientific account relies on models. And those models have specific domains, specific assumptions, and sometimes, well, unresolved foundations.
Okay, let's unpack this. Because to understand where modern cosmology is going, we first have to take a hard look at where human explanation actually started.
Oh, absolutely.
If you go back far enough in human history, our earliest explanations for how the physical world worked relied entirely on stories of intention.
Mythic agency, right?
Yeah, human nature.
I mean, think about being an early human. Why is there a thunderstorm? Well, the sky must be angry.
Right.
Why are the seasons changing? Or why is a crop failing or a disease spreading? It's because invisible spirits are intervening. We looked at the unpredictable terror of nature and just projected our own human-like intentions onto it.
It was a very natural psychological defense mechanism,
Yeah.
We used the familiar language of agency-like human emotion, will, desire to explain the totally unfamiliar behavior of the natural world.
Makes sense.
If a volcano erupts, it is much easier to understand it as the wrath of an underground god than as the complex thermodynamics of tectonic plates.
Obviously.
But slowly, over centuries, that reliance on mythic agency was replaced by the concept of natural law. And I want to trace that shift. Because it didn't just happen overnight. It wasn't as if one day someone woke up and said, hey guys, no more thunder gods. It's actually just atmospheric pressure.
Far from it. The shift began with observation, specifically in astronomy. Early thinkers, like the Ionian philosophers in ancient Greece, they started noticing regularities.
Like patterns.
Yeah, they noticed that eclipses didn't happen randomly whenever a god threw a tantrum. They happened in predictable cycles.
Right.
Centuries later, scientists like Johannes Kepler meticulously mapped the orbits of planets and found they moved in ellipses, following strict mathematical ratios.
And then Galileo comes along.
Exactly. Galileo showed that objects falling to Earth accelerate at a constant rate, completely ignoring what the object was actually made of.
Which culminates with Isaac Newton, right? He looks at Galileo's falling objects on Earth and Kepler's planets in the sky and realizes they are following the exact same unseen rule.
That was the massive intellectual leap. Mechanics connected the motion of a rock thrown in an orchard directly with the celestial motion of the moon.
Wild to think about back then.
And then we saw the same pattern in field theories in the 19th century. Michael Faraday and James Clerk Maxwell replaced the idea that objects had to physically touch to influence each other. They proved that electromagnetic fields operate under strict, invisible laws.
So the whole history of science is just this gradual transition.
A painstaking transition toward recognizing regularities that apply universally, completely regardless of human wishes or prayers or divine intentions.
Let me stop you there, though, and challenge a fundamental definition.
Sure.
Because when we say natural law or scientific law, we have this linguistic habit of thinking about it like a legal code. Like there's a literal cosmic speed limit sign for light or a traffic cop telling gravity how to behave. But a law isn't a command issued to matter by some ultimate authority, is it?
Yeah, let's abandon that traffic cop metaphor completely. A scientific law is simply a compact mathematical representation of dependable relationships among quantities, events, or states. Think of an equation like Newton's force equals mass times acceleration. It is not an instruction manual that the universe reads before deciding what to do. It is just a description of an unbreakable pattern.
Like a recipe that nature always follows.
Well, a recipe's closer, but even that implies a baker. Think of it as the foundational grammar of physical reality. The power of these mathematical laws doesn't come from their authority. It comes from their ability to successfully predict future events, explain past ones, unify seemingly different phenomena, and ultimately give us technological control over our environment.
But if we replace an agent, like a god or a spirit, with a mathematical equation, doesn't that just push the mystery back a single step?
How do you mean?
I'm playing devil's advocate here, but we still have to ask why that specific mathematical law exists in the first place. Like, why this specific mathematical formalism, and why is there a physical reality that bothers to obey it at all? It feels like we solved the what, but completely ignored the why.
You are hitting on the exact philosophical threshold where physics operates. Physics deepens the chain of explanation significantly, but it doesn't necessarily end the philosophical questioning. It forces us to examine what a law actually dictates.
Give me an example.
For instance, let's look at what classical physics did to our understanding of the future. The success of Newtonian mechanics encouraged this idea of a completely clockwork universe, the doctrine of scientific determinism.
This is the idea that if I could somehow know the exact position and momentum of every single atom in the universe right now, I could perfectly calculate the entire future, right? Down to what I'm going to have for breakfast on Tuesday in 10 years.
That was the assumption of the Marquis de Laplace in the 19th century, the ultimate predictable machine.
Right.
If the universe follows strict mathematical laws without exception, then the future is just as fixed as the past. There are no surprises, only a lack of sufficient data.
But we know that's not how reality actually plays out. Even without getting into quantum weirdness yet, just on a human scale, the weather forecaster can't even tell me if it's going to rain next weekend with 100% certainty.
Which highlights a crucial distinction. Determinism in the equations is not the same thing as practical predictability for observers.
Okay, clarify that.
Even in a purely classical Newtonian deterministic universe, chaotic systems exist. Chaos theory demonstrates that in complex systems, tiny, microscopic uncertainties in the initial data are amplified so rapidly that long-range forecasting completely fails.
Ah, the famous butterfly effect.
Exactly. The butterfly flapping its wings in Brazil, setting off a tornado in Texas. If you are calculating the weather and your measurement is off by 1/1,000,000th of a degree, that microscopic error multiplies exponentially through the equations of fluid dynamics. Yeah, within a week, your prediction is completely useless. So just because the universe might be governed by strict laws, it does not mean it is predictable to us. And, as we will discuss later, when you add quantum mechanics to the picture, which makes probability central to the very fabric of reality, that strict, predictable clockwork shatters entirely.
I know if you're listening in your car right now, you might be thinking, okay, but what does this mean for me? Like, for human scale? Because if we extend this lawful mechanical description to everything, including the neurons firing in our human brains, does that mean our choices, our emotions, our sense of free will are just illusions? Are we just complex, chaotic chemistry sets convincing ourselves we are making choices?
That is a very common existential panic, but it relies on a misunderstanding of how scientific description works. Extending lawful chemical descriptions to human brains doesn't eliminate human meaning or agency. It's a matter of understanding layered descriptions.
Layered descriptions.
Yeah. Think about it this way. Unpredictability in chaos theory doesn't prove we have free will, nor does determinism prove we are mindless robots. A physical account of human decision-making operates at several distinct levels simultaneously.
Walk me through those layers.
At the lowest level, you have the fundamental interactions of quarks and electrons.
Okay.
Move up a level, you have the molecular chemistry of neurotransmitters like dopamine and serotonin.
Right.
Move up again, you have the biological wiring of neural networks in your frontal lobe. Move up to the macro level, you have the psychological reasons you make a choice, influenced by your social context and personal history.
So if I choose to drink coffee instead of tea, the physicist says my electrons did it, the biologist says my neural pathways did it, and the psychologist says I did it because I was tired.
And they are all entirely correct. These are legitimate layer descriptions of the exact same event. They don't cancel each other out just because they aren't interchangeable. That makes a lot of sense.
Yeah.
You wouldn't use the equations of quantum chromodynamics to predict the stock market, just as you wouldn't use psychology to explain the orbit of Mars. Recognizing that the brain follows physical laws doesn't render the psychological level of description fake. It simply grounds it in physical reality.
That actually makes me feel a lot better.
Right.
But to really grasp how we use these laws and layer descriptions, we have to take a hard look at how we process reality itself. Because we don't have a direct, magical link to the universe. We can only perceive things through our very limited biological senses and the instruments we build.
Yes.
Which introduces a concept that is central to this entire discussion and, frankly, central to modern science: model-dependent realism.
Model-dependent realism is the crucial foundational framework for handling the relationship between our scientific theories and objective reality. The core truth here is that human beings never encounter the world without mediation.
Mediation, like a middleman.
Right. Our perception is not a direct, transparent window to reality. It is a highly processed, biologically constructed representation.
Wait, elaborate on that. What do you mean by biologically constructed?
Well, think about human vision. You do not actually see the room you're in.
I feel like I do.
But you don't. Photons bounce off objects, enter your pupil, hit your retina, and trigger electrical impulses. Those impulses travel up the optic nerve to the visual cortex at the back of your brain.
Okay.
Your brain then takes those scattered electrical signals, fills in the blind spots, interprets the shadows to guess at 3D depth, and constructs a mental image. The picture you experience is a model built by your brain. You never have access to an unmediated absolute reality outside of the models your brain and your instruments construct.
I was actually thinking about an analogy for this last night. Imagine you need to understand a massive, complex city. You could use a road map to navigate the streets, or you could use a subway diagram to ride the trains, or a topographical map to see the hills.
That's a great example.
Now, none of those maps contain every single feature of the city. A subway map completely distorts geographical distance like. It makes stations look equally spaced out just to make the connections clearer.
Let's expand on that analogy because it is incredibly useful. The subway map suppresses an enormous amount of true information, like the location of parks, the traffic lights, the actual shape of the tunnels.
Right.
But it suppresses that information to serve a specific predictive purpose. It is not wrong just because it isn't an exact one-to-one replica of the city.
Right. If it were a one-to-one replica, it would just be the city itself, and it would be totally useless as a map.
Exactly. And advanced scientific theories operate the exact same way, though they go much further by generating strict quantitative expectations for unknown outcomes. The layered description is absolutely unavoidable.
Give me a scientific example.
Take thermodynamics, for example. It is a highly successful model that talks about pressure and temperature. It allows us to build steam engines and refrigerators, but it completely ignores the individual trajectory and velocity of every single molecule in a gas.
Because tracking 1 trillion molecules is impossible and totally unnecessary if you just want to know how hot the room is.
Precisely. The choice of variables determines which patterns become visible and which questions become mathematically tractable. Evolutionary biology discusses natural selection and genetic drift without trying to reduce the mating habits of birds to interacting particle trajectories.
But hold on, if our perception is just a biological construct, and our science is just a series of simplified maps and mathematical models, how do we know any of it is actually true? Like, how does a scientific model earn our confidence rather than just being a nice story we tell ourselves?
A model earns confidence through a very strict, unforgiving set of criteria. First, it must be internally coherent-like. The math can't contradict itself.
Right.
Second, it must be economical. It cannot require an absurd number of arbitrary assumptions to make it work. Third, it must be consistent with all existing observations. And fourth, and most importantly, it must be capable of making successful, testable predictions about future observations.
Okay, but here is where things get sticky. What happens when you have two completely different models that describe the same phenomenon, and they both make the exact same accurate predictions?
I know where you're going with this.
Yeah, I am thinking specifically of quantum physics. where sometimes we model light or matter as discrete little particles, and other times we model them as continuous spreading waves.
That is the exact scenario where model-dependent realism does its heaviest philosophical lifting. In the everyday world, something is either a rock, a particle, or a ripple in a pond, a wave. But in the quantum realm, light exhibits properties of both, depending entirely on how you measure it.
Right.
If two models, like the wave picture and the particle picture, both make accurate, observable predictions within their overlapping domains, we simply cannot declare one to be uniquely real just because it feels more intuitive to our primate brains. We have to accept that both are valid models of reality within their specific contexts.
I have to challenge this because I can hear the audience bristling right now. Does this mean anything goes? If we can just swap models based on what works, is reality just whatever we subjectively decide to model it as? Because that sounds dangerously close to relativism, where actual objective facts don't matter, and my personal truth is just as good as your math.
I am incredibly glad you brought that up, because that is the most dangerous misunderstanding of model-dependent realism. Model dependence is a rigorous discipline of comparison. It is completely answerable to hard evidence, logical consistency, and new experimental tests. It is emphatically not a license for arbitrary belief or pseudoscience.
So my personal model that the Earth is flat isn't valid just because it works for me when I walked out of the grocery store.
Exactly. Going back to your map analogy, if your personal model of the city says there is a solid bridge where there is actually a deep river, and you try to drive your car across it based on your subjective model, your car will sink. The model is constrained by reality. Model-dependent realism just admits that we only know the river is there because our sensory models and our scientific maps successfully detect it and predict the sinking of the car. We don't have godlike access to the river itself.
That makes perfect sense. The models are tethered to the data. And this realization that our models dictate our understanding and that we must be ruthless about updating them when the data changes is perfectly illustrated by the biggest scientific earthquake of the 20th century. What happened to our model of space and time?
Oh, absolutely.
Because before Albert Einstein came along, the scientific model was basically that space and time were an absolute rigid stage.
Yes, the Newtonian view. And it matched human intuition perfectly. In Newton's model, space was an empty, static, three-dimensional arena, and time was a universal, invisible clock ticking at the exact same rate for everyone, everywhere in the universe. Matter and energy just moved around on this unchangeable stage. The stage itself was completely unaffected by the actors on it.
But then Einstein realizes that the speed of light is constant, no matter how fast you are moving. And to make that math work, he has to completely break the clock.
In 1905, special relativity completely linked spatial and temporal measurements to the motion of the observer. Your measurement of how long an object is and how fast time is ticking depends entirely on how fast you are moving relative to the object. The absolute universal clock was shattered.
Which is already a huge conceptual shift. Time is relative. But then 10 years later, general relativity comes along and does something even more radical to the stage itself.
General relativity completely reinvented our model of gravity. Newton modeled gravity as an invisible tether, a force pulling objects together across the static arena of space. Einstein modeled gravity as the dynamical geometry of space-time itself.
Explain the mechanics of that. How can geometry be a force?
Think of space-time not as an empty room, but as a flexible fabric, like a four-dimensional trampoline. If you place a heavy bowling ball, representing a star like our sun, in the middle of the trampoline, the fabric sags and curves around it.
Right, creating a dip.
If you then roll a marble representing a planet like Earth across the trampoline, it doesn't move in a straight line. It follows the curve created by the heavy ball circling it.
So the Earth isn't being pulled by an invisible rope. It's just coasting along the curved grooves of space.
Yes. The physicist John Archibald Wheeler summarized it perfectly. He said, "Matter tells spacetime how to curve, spacetime tells matter how to move. Gravity is the shape of the universe."
So the stage itself is evolving. It's bending, stretching, and warping. The arena is actually part of the play.
And the conceptual importance of this for cosmology cannot be overstated. It means that the history of the cosmos isn't just a history of galaxies moving away from each other through pre-existing empty space. It is the history of space-time itself expanding.
Wow.
This model successfully explains everything from the slight, previously unexplainable shift in the orbit of Mercury to the way massive galaxy clusters actually act like magnifying glasses, bending the light from galaxies behind them, a phenomenon called gravitational lensing.
Okay, here's where it gets really interesting and where the math starts to corner us. General relativity is a classical theory. It is a model that works beautifully for massive things, stars, galaxies, black holes. But if the universe is expanding today, that means it was smaller yesterday.
Logically, yes.
And if we run the tape backward, extrapolating the expansion of the universe back to the very, very beginning, the Big Bang, we hit a massive catastrophic problem with the model, don't we?
We do. If you extrapolate the equations of general relativity backward in time, the universe gets smaller, denser, and hotter. Eventually, you approach a regime where all the matter and energy in the observable universe is compressed into an infinitesimally small volume.
Right.
At that point, the density and the curvature of spacetime becomes so extreme, approaching infinity, that classical mathematics simply breaks down.
What do you mean breaks down? Does it just say error?
Well, in physics, when an equation outputs infinity, it is usually nature's way of telling you that your model has reached the end of its useful domain. A singularity, a point of infinite density, isn't a physical object we think actually exists. It is the mathematical point where general relativity throws up its hands and ceases to function. It reveals the desperate need for a deeper, more comprehensive theory at precisely the point where the questions about our cosmic origin become the most intense.
So, if Einstein's equations literally break down at the origin of the universe, what tool do we pick up to look closer at that exact beginning?
We have no choice but to introduce the other great pillar of 20th century physics, quantum mechanics. Because at that microscopic scale, compressed into a space smaller than an atom, the early universe was governed entirely by quantum rules.
I have to admit, whenever we talk about quantum mechanics, it always sounds a bit like magic. We hear things like particles being in two places at once, or cats in boxes being alive and dead. It sounds like science fiction. But quantum theory isn't just some tiny mathematical correction we tack onto classical mechanics, right? It's a completely different grammar for how physical reality works.
It changes the entire foundation of how physical possibilities combine. Let's contrast it. In classical physics, if you throw a baseball from point A to point B, that baseball takes a single, defined, calculable path through the air. You can film it.
Right.
In quantum physics, when you track a subatomic particle moving from point A to point B, you cannot assume a single trajectory. The system involves complex amplitudes, probabilities, and most importantly, interference.
Let's break down interference, because it is crucial.
When we say interference, we mean that different possible alternatives can actually interact with each other before a final probability is calculated. If you shine light through a barrier with two slits, the light wave passes through both slits, and the two resulting waves overlap.
Like ripples on a pond.
Exactly. Where the crests meet, they amplify into a bright spot. Where a crest meets a trough, they cancel each other out, leaving a dark spot. This creates an interference pattern.
But the wild part is, if you fire individual single particles of light photons, one at a time, through those two slits, over time, they still build up that exact same striped interference pattern on the wall behind them. How is a single particle interfering with itself?
That is the mystery that Richard Feynman sought to solve mathematically. He introduced this incredibly powerful framework called the sum over histories, or the path integral formulation.
Walk us through the mechanics of Feynman's sum over histories. How does it calculate where that particle lands?
Feynman proposed that to calculate the quantum probability of a particle going from point A to point B, you don't just calculate one straight-line trajectory. Instead, you mathematically sum up the contributions from every single possible path connecting those 2 points.
Every possible path. You mean a path that goes straight through the slit, a path that loops around the laboratory, and a path that bounces off the moon and comes back?
Yes. Mathematically, the particle takes all of them simultaneously. Every single history is assigned a number, a phase based on the physical action of that path. You add all those numbers together to get the final probability of finding the particle at point B.
Okay, stop right there. When you say all possible histories, I need to jump in and prevent a massive misconception. I've read enough pop sci and watched enough movies to know where people's minds go. We are not talking about literal, fully formed fictional timelines branching off. Like, there isn't a literal parallel universe hovering in the room where the particle went left and another where it went right, or a universe where I had cereal instead of toast this morning.
You are exactly right to flag that, and it is vital we dispel that sci-fi interpretation. A history in Feynman's path integral is a mathematical configuration within a calculation. It is a probability weight. It is not a fully formed parallel narrative with conscious beings in it. Quantum possibility is highly structured and constrained.
So how does a baseball, which is made of trillions of quantum particles, manage to just take one normal path through the air if its particles are mathematically taking every path to the moon and back?
Because of how those phases add up. What Feynman's math shows is that wildly varying, chaotic, macroscopic paths have phases that spin wildly and cancel each other out.
Like the crest of one wave hitting the trough of another. They erase each other mathematically.
Precisely. The extreme paths mutually destruct in the calculation, but the paths that are very close to the classical straight-line trajectory have phases that align. They reinforce one another. So classical observable motion, the single path we actually see the baseball take, emerges as a direct result of these nearby quantum contributions amplifying each other while the crazy paths cancel out. It provides an astonishingly beautiful mathematical bridge from the weirdness of quantum particles to the classical solid world we experience.
So, if quantum physics says that microscopic systems have a sum of possible histories, how on earth does that apply to the origin of the universe? Because when we talk about the Big Bang, the system we are talking about isn't a single photon in a lab. It is the entire cosmos.
That is the incredibly difficult leap of quantum cosmology, because usually in quantum mechanics you have an external observer or a laboratory apparatus measuring a system from the outside. But you cannot stand outside the universe to measure it. The observer is inside the system.
Right.
So how do you apply quantum rules to the whole cosmos? This leads us to a radical methodology called top-down cosmology.
Top-down cosmology. Let's contrast this. Ordinary historical reasoning is bottom-up, right? We assume a single starting point in the past, a set of initial conditions, and we run the equations forward in time to see how the universe develops into what we see today.
Correct. But top-down cosmology flips the arrow of deduction completely. Instead of assuming one unique microscopic route from an unknown past, top-down cosmology works backward. It asks, how are the probabilities for past histories mathematically conditioned by the precise observational situation we find ourselves in present day?
Wait, re-explain that. We use the present to change the past.
Not change the past in a causal time travel sense. We use the present to weight the probability of the past. In quantum theory, a system doesn't have a single defined past until it is measured. The conditions present right now, the fact that we observe a universe with 3 spatial dimensions, a specific background radiation temperature, and expanding galaxies, those present facts act as constraints.
Okay.
We apply Feynman's sum over histories, but we only sum the histories that actually end up creating the universe we are measuring right now.
I want to use an analogy here to help visualize this, but correct me if I stretch it too far. Imagine a massive, almost infinite library of rule-governed computer simulations running on a server. A rule set defines how the simulations are allowed to develop. The initial settings dictate the countless variations of particular runs.
Owing you so far.
But an observer who wakes up inside one of those specific runs will only encounter the histories that are mathematically compatible with their own existence and their current surroundings.
That analogy helps clarify a lot about selection effects, but we must immediately name where it fails. We must not stretch this simulation analogy into evidence for an external programmer or a literal computer universe running on a hard drive. The physics absolutely does not require an intelligent creator for the simulation.
Right.
The useful point of your analogy is purely structural. It helps us separate the distinct roles of the laws, the initial conditions, the probability weights, and the observations.
Right. It's about the physical conditioning of data. It's not saying that a conscious human observer magically manufactures a cosmic past with their mind just by looking at a telescope.
Precisely. Observers are physical systems embedded in the universe. Our current astronomical data constrains the viable mathematical models of the past. Alternative quantum histories only matter insofar as the framework assigns them mathematical weight, and they funnel into the precise conditions we actually see today.
But this brings us to a massive roadblock, the boundary problem. If we are working backward, building these mathematical cosmological models, they don't just need equations for how things change over time. They need boundary conditions. They need a state to start from.
Yes, the initial state.
If the laws of physics allow for a nearly infinite sum of different possible quantum histories, why is our universe described by this specific history, with these specific boundaries, and not another one?
The early universe makes this incredibly tricky. We can't just take the assumptions from our everyday laboratories and push them to arbitrarily high energies near a singularity. A scientific proposal about cosmic origin is, therefore, fundamentally a proposal about boundary conditions. What was the state of the universe at time zero? This is where the famous Hartle-Hawking no-boundary proposal comes into play.
Stephen Hawking and James Hartle. I've read about this, and it is one of those ideas that is just beautifully, profoundly mind-bending. How did they attempt to solve the problem of time zero?
They treat the entire universe quantum mechanically, and they seek to calculate its wave function by summing over all possible geometries. But the mathematical trick, the stroke of genius, is that they sum over regular, continuous geometries that do not have a past boundary.
A universe without an edge. What does that actually mean?
In their simplified mathematical models, they use a concept called imaginary time. As you extrapolate backward, getting closer and closer to what we would traditionally call the beginning or the singularity, the distinction between a temporal direction time and a spatial direction space changes smoothly. Time spatializes. It becomes just another dimension of space.
This is the famous North Pole analogy, isn't it?
Yes. Think of the surface of the Earth. If you walk south, you eventually hit the South Pole. If someone asks you what is further south than the South Pole, the question itself is meaningless. The geometry of the sphere removes the edge. There is no sharp boundary or cliff at the pole. It is just a coordinate limit.
So time behaves like a dimension of space. The concept of a time before the Big Bang just loses its physical meaning because you've hit a smooth geometric bowl that doesn't contain a bowl. It's closed, but it has no edge.
That is the exact mathematical intuition. It aims to make the universe finite, yet completely self-contained, without needing to place an earlier moment or an external cause outside the mathematical model.
I just want to let the listeners sit with the weight of that for a second. The idea that time itself dissolves into space, meaning the universe didn't have a sharp start point that requires a trigger. It's breathtaking. But let's be responsible here. How proven is this?
We must carefully label our confidence here. While general relativity and quantum theory are exceptionally well tested and supported by millions of experiments, the no-boundary proposal is an active, unconfirmed theoretical research program.
Okay, good to know.
It is an elegant mathematical hypothesis. It is not an experimentally settled fact. Defining these quantum gravitational path integrals is technically brutal, and theoretical physicists actively debate the approximations and predictions it generates.
But even as a hypothesis, it illuminates the kind of explanation cosmology is actually looking for. It shows that a beginning doesn't necessarily have to be a sharp, jagged event caused by something at an earlier time if time itself is an internal property of the physical system being created.
Right. But to truly understand how time could act like space at the extreme energies of the beginning of the universe, physicists need a mathematical language they don't fully have yet. A unified framework. A working theory of quantum gravity that brings general relativity and quantum mechanics together without producing infinities.
Unification, the holy grail of theoretical physics. If we look back, the entire history of physics is basically a history of showing that things that look totally different are actually manifestations of the exact same thing. Electricity and magnetism look different, but Maxwell unified them into electromagnetism. Then the weak nuclear force was added to make the electroweak theory.
Leading eventually to the Standard Model.
Exactly, which successfully organizes all known subatomic particles and 3 of the 4 fundamental forces.
But gravity is the stubborn, irreconcilable holdout. General relativity, the smooth, continuous geometry of spacetime, simply does not merge straightforwardly with quantum field theory, the jittery, discrete, probabilistic world of particles.
They just don't play nice.
At all. If you try to combine their math to describe a black hole or the Big Bang, the equations break down. A true theory of quantum gravity has to recover both frameworks perfectly, where they are known to work, while also providing consistent, finite predictions in those extreme regimes.
And unification is incredibly attractive philosophically because it reduces the number of independent assumptions you have to make. You don't want 5 different rulebooks, you want one master rulebook. But as we've learned with model-dependent realism, mathematical elegance isn't the same as hard evidence. So what is the leading candidate for this ultimate unification?
For several decades, the leading mathematical framework has been string theory. It attempts to resolve the infinities by replacing the idea of fundamental, zero-dimensional, point-like particles with tiny, one-dimensional, microscopic excitation strings.
So instead of a dot, it's a little rubber band.
Conceptually, yes. And just like a violin string can vibrate in different patterns to produce different musical notes, these fundamental strings vibrate in different patterns. The specific vibrational pattern determines the properties of the particle we observe: its mass, its electrical charge, its spin. So an electron is just a string vibrating one way, and a quark is a string vibrating another way.
That sounds beautifully simple. But to make the math of string theory actually work without generating anomalies, it demands a very heavy price, doesn't it? It requires extra dimensions.
It does. The math simply does not work in our standard 3 dimensions of space and 1 of time. It requires dimensions beyond what we can perceive, typically 10 or 11 dimensions in total. It also introduces extended objects of higher dimensionality, commonly called branes, short for membranes. You can have 2-dimensional branes, 3-dimensional branes, all interacting in this higher dimensional space.
And this evolved in the 1990s into something even more comprehensive called M-theory.
Yes, during what physicists called the second superstring revolution, theorists discovered deep mathematical relationships called dualities that proved that 5 previously distinct competing versions of string theory, along with an 11-dimensional theory called supergravity, were not actually different theories.
Oh, wow.
Yeah, they were just different mathematical limits or different perspectives of a single, deeper underlying structure. They called it M-theory. This duality is actually a perfect high-level example of model-dependent realism. 2 mathematical descriptions that look radically different on the surface can actually encode the exact same physical reality in their overlapping domains.
I want to be very clear for the listener here, because pop science media often runs completely wild with this, presenting it as established fact.
Yeah.
M-theory is not a single finished equation that you can write on a chalkboard, right?
Absolutely not. It is a vast, incomplete research framework. It boasts profound mathematical achievements, but it only exists in partial formulations. We do not have the fundamental equations of M-theory. It is not a complete theory where every prediction is known, and it has not been directly experimentally verified.
And one of the wildest, most philosophically disruptive things to come out of this framework is the concept of the landscape. If M-theory has 11 dimensions, and we only see 4, 3 space, 1 time, where are the others? What is the landscape of M-theory?
Because M-theory requires these extra dimensions, but we don't observe them, physicists hypothesize they must be curled up or compactified at microscopic scales. Imagine a garden hose from a distance. It looked like a one-dimensional line. But if you look closely, it has a circular cross-section. It has a second dimension curled up around it.
Okay, so these extra 7 dimensions are rolled up so tightly we can't detect them.
Right. But there are millions of different geometric ways to compactify those dimensions. They can be twisted and folded into incredibly complex shapes called Calabi-Yau manifolds. And here's the kicker. The specific shape of those hidden dimensions determines how the strings vibrate. And how the strings vibrate determines the masses of the particles and the strengths of the forces in the macroscopic world.
Wait. So depending on how those invisible extra dimensions happen to be rolled up, the actual laws of physics we experience, like the mass of an electron, the exact strength of gravity, the properties of light, would be completely different.
Exactly. Different compactifications yield vastly different low-energy physics. And the math of M-theory allows for an astonishingly huge number of possible compactifications. Some estimates put it at 10 to the 500th power.
That's incomprehensible.
It creates an enormous landscape of possible physical configurations. It is a vast collection of possible laws of physics, all mathematically permitted by the fundamental theory.
But wait, if M-theory allows for an almost endless variation of physical laws, how did we end up in the exact specific one that allows us to exist? Because our universe seems incredibly, suspiciously specific.
You've just hit on one of the most intense, fiercely debated problems in modern cosmology, the problem of fine-tuning. Many fundamental constants in our physics appear to fall within incredibly narrow, precise ranges.
Give me an example of how narrow.
If the strong nuclear force which hold atoms together were just slightly stronger or slightly weaker, carbon wouldn't form in the hearts of stars. No carbon, no organic biology. If the gravitational constant or the expansion rate of the universe were slightly different, the universe would have collapsed back in on itself immediately. or expanded so fast that galaxies and stars could never clump together.
Wow.
Our universe appears exquisitely fine-tuned to permit stable structures, complex chemistry, and ultimately carbon-based life.
So how do physicists explain that? Is it just blind necessity? Is it incredibly lucky chance? Or is the theory just incomplete and we'll eventually find a math equation that proves it had to be this way?
One prominent framework for addressing this is the anthropic principle. In its most restrained, scientifically valid form, it is simply an observational selection effect. It states that any beings capable of building telescopes and making measurements must, by definition, naturally inhabit a universe whose conditions are compatible with their existence.
It's like a fish marveling that the ocean happens to be perfectly made of liquid water. If the ocean were made of solid rock, the fish wouldn't be there to marvel at it. The observation is biased by the existence of the observer.
That's a great way to look at it. It is logically valid. But as an explanation, it feels somewhat empty unless it is paired with a broader physical framework. Because to have an observational selection effect, you usually need a massive ensemble of different options to select from. If you only roll the dice once and get the exact 1,000,000-to-1 sequence needed for life, the anthropic principle doesn't explain the luck.
Which brings us to the most controversial concept of all, the multiverse. If the landscape of M-theory allows for 10 to the 500th powered different laws of physics, are we talking about a literal multiverse where all those variations physically exist out there in space and time?
This is where we must tread with extreme philosophical caution. The multiverse is not a single unified proven theory. It is a family of speculative hypotheses. You have quantum interpretations, you have eternal inflation creating bubble universes, and you have the cosmological landscape of string theory.
Okay, so it's a bunch of ideas.
Right. In the context of M theory, if a physical generating mechanism like rapid cosmic inflation creates many different isolated regions of space, and each region realizes a different mathematical configuration from the landscape, then the specific laws we measure locally in our universe are just environmental outcomes.
They aren't the uniquely fixed universal laws of all reality. They are just the local weather in our specific cosmic neighborhood. And we obviously live in the hospitable neighborhood because otherwise we wouldn't be having this conversation.
Yes, that solves the fine-tuning problem by brute force multiplication. But we must be rigorous here. Explanatory game requires more than just mathematically multiplying possibilities. To be considered hard science and not just speculative metaphysics, a multiverse hypothesis needs a physical generating mechanism, a probability measure to compare outcomes, and, crucially, it needs indirect testability.
Testability is key.
We may never have direct access to look into other universes, but the theory generating them must predict unique, observable features within our own universe. The multiverse is a conditional research idea. Current evidence does not justify presenting it as an observed, settled fact.
That is such an important, sobering distinction. Physicists aren't just making up other universes because they are bored. They're following the mathematical consequences of theories like inflation and string theory, but they are rightfully acknowledging those theories are unconfirmed. And this brings me to another phrase that pop science articles absolutely love to use, and that causes endless public confusion: creation from nothing. We constantly see these clickbait headlines like, "Quantum physics proves the universe appeared from nothing."
Yes, and that phrase is rhetorically very powerful, but it is conceptually highly unstable and often misleading. When a philosopher, a theologian, or even just an everyday person hears the word nothing, they think of absolute, unadulterated philosophical non-being. The complete absence of absolutely everything. No space, no time, no math, no rules. But in quantum field theory, a vacuum is emphatically not non-being.
So when cosmologists talk about the quantum vacuum, what are they actually talking about?
A quantum vacuum is a highly active physical state. It has defined mathematical structure. It has fluctuating fields, energy, and virtual particles constantly popping in and out of existence. It is a bubbling soup of potential.
So when physicists say the universe was created from nothing, they don't mean a blank philosophical void.
No. In quantum cosmology, nothing might just mean the absence of a classical space-time boundary, like we discussed with the no-boundary proposal. Or it might mean a quantum state defined by a specific mathematical path integral. Every single scientific use of the word nothing already presupposes complex mathematical rules and a pre-existing framework of physical possibility.
So the physics isn't actually saying that absolute non-being somehow magically birthed the universe. It's saying that classical spacetime might not require an earlier classical temporal cause. The cosmic history, governed by quantum gravity, could be mathematically self-contained.
Precisely. And this leads us to the ultimate philosophical frontier. The authors of the source material we are exploring today, Stephen Hawking and Leonard Mlodinow, argue quite forcefully that a creator is unnecessary within their specific physical account. They suggest the universe can naturally and spontaneously arise from these quantum gravitational laws.
And as an independent deep dive, we need to navigate this carefully and neutrally. Because stating that a creator is mathematically unnecessary within a specific theoretical model is very different from proving that all metaphysics or religion is definitively false.
That is the critical epistemological distinction. Physics can and does heavily constrain metaphysical proposals. It shows us what natural processes are incredibly capable of accomplishing, and it completely revises our everyday concepts of time, space, and causality.
Right.
But we must distinguish the conclusion that a mathematical mechanism is self-contained from the stronger, philosophically unsupported claim that every possible religious or metaphysical interpretation of existence has been experimentally disproved by a telescope or an equation.
Right. Because if the universe arises from the laws of gravity and quantum mechanics, someone can simply ask, well, where did gravity come from?
Exactly. Some concepts of creation in theology and philosophy are about ontological dependence. Like, why there is something rather than nothing at all, not about a temporal mechanism striking a match at the beginning of time. Whether the mathematical laws themselves require an explanation or exist as Platonic truths is a further philosophical question that equations alone cannot resolve.
This brings us to the human impact of all this knowledge. When you look at the sheer scale of what we've discussed, the unfeeling mathematical laws, the vast landscapes of M-theory, the possibility of a multiverse, the insignificance of our tiny planet, it can induce a kind of profound cosmic vertigo. Does this cosmic modesty, this realization that we aren't at the physical center of a uniquely designed universe, does it erase human meaning?
It absolutely does not have to. A comprehensive physical description changes how we think about our context, but it doesn't dictate a nihilistic ethical conclusion. If humans are the products of an unimaginably vast cosmic and biological history, our capacities for care, for inquiry, for cooperation, and for creativity remain incredibly real, tangible features of that history.
Scientific accounts explain the mechanisms of reality. But values, meaning ethics, those are human judgments about what we protect, pursue, and cherish.
Exactly. And reducing human meaning to a gap in physical explanation, arguing that we only have significance in the most science hasn't explained yet, is a very dangerous game. It makes human meaning vulnerable to every new scientific advance. Understanding our place in a lawful, immense cosmos can actually support profound intellectual humility. It invites awe at the intelligibility of nature.
The fact that we can understand it at all is amazing.
Exactly. The fact that conscious, evidence-seeking life exists and can build mathematical models to understand the universe far beyond our everyday biological experience has an unusual and profound significance to itself. It shouldn't make us feel small. It should deepen our appreciation for just how fragile, rare, and incredible knowledgeable communities really are.
That is a beautiful and grounded way to frame it. Okay, we have covered an immense amount of ground today. We started with humanity's gradual shift from projecting mythic agency onto nature to uncovering classical natural laws. We explored the limits of determinism and chaos. We descended into the weird, highly structured grammar of quantum possibilities and Feynman's sum over histories.
It's a long journey.
It really is. We worked backwards, using the calculations of top-down cosmology, explored the boundary problem, and looked at the bleeding-edge limits of M-theory, hidden dimensions, and the vast, conditional landscape of a potential multiverse.
And through it all, we applied the rigorous lens of model-dependent realism, maintaining strict accountability to predictive evidence while acknowledging that our pictures of reality are always mediated by our models.
So I want to leave you, the listener, with a final provocative thought to mull over as you go about the rest of your day. If humanity does one day achieve it, if we find that final, elegant, unified physical theory of quantum gravity, would it actually explain existence completely? Or would it simply move the deepest question to another level, leaving us to look at that perfect unified equation and ask, why is that specific mathematical framework the one that breathes fire into the equations and makes a universe for us to describe?
It remains the ultimate open question.
It really is. Now, we want to respectfully identify the source of the incredible physical concepts and historical context we explored today as The Grand Design by Stephen Hawking and Leonard Mlodinow. We want to be exceptionally clear that this production is an independent Cosmora HQ companion deep dive, and we highly encourage you to obtain the original work legally to explore these foundational ideas directly from the authors themselves. Thanks for taking this massive cosmic plunge with us today.